Hi, welcome back. We are continuing our discussion about boundary value problems, that is the mathematical version of elasticity, which starts with the equations of equilibrium for a homogeneous isotropic Hookean material. So let us quickly look at our task. Our task now is to find the displacement field that satisfies this equation inside the domain, that is not including the skin. I'm telling you, it's just the inside. Okay, inside it has to satisfy gradient of divergence of u plus 1 minus 2 nu times divergence of gradient of u plus 1 minus 2 nu over mu equal to times b equal to 0. Our stress strain relationship looks like this: mu over 1 minus 2 nu times 1 minus 2 nu times gradient of u symmetric plus 2 nu times divergence of u times identity is the stress, subject to the boundary conditions. Notice that slowly we are trying to eliminate all our pictorial stuff and we are trying to convert it entirely into symbolic things. Okay, this is what we have to solve. This is a second order differential equation and we have to solve this subject to these boundary conditions. How do we do this? Our approach is combination of mathematical skill and physical insight. You need to be able to do some mathematics and combine it with physical insight. You cannot do just think of it as a boundary value problem and try and do it. That's not how it works. It's not a purely mathematical problem. The number of things that you have to do with physical insight. Typically, we use some mathematics to figure out what we can solve. Okay, what kind of problems can we solve? How can we solve it? What are the techniques? You know, if you take a math class, math 602 for example, and it talks about, you know, Fourier series, you know, all these things, those are solution techniques. And we have to adapt our problem to make it simpler. Typically, this part is called defeaturing. Remove complications mainly from geometry. Okay, but it cannot be all complications, inessential complications. And the question of what is inessential and what is essential comes to a combination of math and physics. So there are certain things that you can eliminate, certain things that you cannot, and you have to know which is which. Okay, so let's look at an example of mathematical skill. Turns out that if you look at your differential equations and you can do what is called mixing and matching. This is because of the mathematical structure of the differential equations. For linear differential equations, you can have the principle of superposition. If u1 and u2 both satisfy the differential equation in omega, it should not be w, it should be omega, then alpha times u1 plus beta times u2 will also satisfy the differential equation for constant alpha and beta. So you can mix and match two solutions to the differential equation, but the caveat is they will not satisfy the same boundary condition. So you have to be careful about what happens at the boundary. So I told you, it's the skin of the potato that gives you the trouble. It's not the inside of the potato. Okay, so yes, it will satisfy the differential equation, but be careful about boundary conditions. And you have to look at what will the combination of these two things satisfy. So the advantage of this very simple principle of superposition is the fact that you can do a catalog of solutions. And then you can mix and match what you want. So the advantage, why do we like linear equations, is because you can do catalog of solutions and mix and match. So it's only a matter of saying I have enough number of solutions, I can take this and add it to that and create a new one. And once you have a new solution for these kinds of things, you can then mix and match and do certain things and get more and more solutions. I'll show you a catalog in class. This is the catalog of solutions for fracture, and you will see how this works. And you have seen some of this in your earlier classes when you looked at catalog of solutions for stress concentration and things like that. Okay, that's a big thing. So this is an example of mathematical result, and so this is a very simple one, but it nevertheless gets you the power of mathematics. Now let's look at the power of a physical example. What's the power of physical insight? It says, let us assume you have a homogeneous isotropic neo-Hookean material. If you replace the tractions on part of the boundary with another distribution, what do I mean? Here is one part of the boundary, and let us say you have tractions that are like this, uniform traction, and you replace it with a single force for simplicity, or you replace either this way or that way. What it is that it has to have the same net force. So if the total force due to this is 10 pounds, this had better be 10 pounds. And it has to have the same net moment, which means that if I pick a point here and take moment of all these forces, it should be the same as the moment of this force around that same point. So this is called equivalent. Same net force and same net moment. And why net force and net moment, I'll talk to you about that later. But right now it has to have the same net force and net moment. Then if you want to find stresses far away from this region, let's say you want to find the stress here, it will not be affected by much. It doesn't matter whether it is this distribution or that distribution, you will get the same answer, more or less. So what happens is, if I find out that mathematically it's easier for me to solve this than this, I will replace this problem with that problem and say sufficiently far away things are okay. This is called Saint Venant principle. Actually, it should be called Saint Venant working hypothesis, and it is by one of the most famous elasticity people, and his name is AJCB Saint Venant. He was a great civil engineer, and he did a lot of problems. He found a lot of elasticity solutions by a particular technique. We will see a lot of them, and most of them are still in use. But he also had some difficulties and problems, and that's a whole another thing. But my point to you is, this is an example of physical insight. You cannot prove this very rigorously mathematically unless you make very strong assumptions about all kinds of things. And what do you mean by sufficiently far away? All of these things are vague, and turns out doesn't work very well if the body is inhomogeneous and its elastic constants are far from a corresponding isotropic elastic constants. What I mean by that is, if really shear modulus and Young's modulus are really far away from each other, or one of the directions is very, very stiff, so on and so forth, you cannot use this. Okay, but this is an example of a physical insight. Thank you.